be okay if we record it?
Oh, yeah.
Yeah, okay.
By all means.
So there's the, let me go this high. Or we can.
Everybody awaits in anticipation. Joe said it would probably be a good idea to wait about 5 minutes.
Yeah. I only have 200 slides. So.
Pardon? Well, whatever happens, happens.
Yeah. At least I'm not keeping people from lunch.
True, absolutely. But again, the idea of Zoom is the big thing. I mean, people watch from home. Why not?
Oh, no.
Oh,
What does that mean? Does that mean something?
It's written.
they move the chair.
I have to come down here because of my eyes.
We're gonna wait exactly on time.
Spotlight on. Sure, you can do that. Got everything going. Good for you.
Yeah. And just think of the millions of viewers watching on
Yeah.
Zoom.
I should feel like Geraldo or
Yeah.
like Geraldo. Yeah. So many viewers. You used to get in fights, right?
Maybe we should put the lights on. Don't you think so?
You want some lights on? I can do that. Yeah, thank you. Yeah, sure. I wonder what this middle button does.
Don't press that.
Oh, there is a component. Yeah, that's too much too, right? Yeah.
Whatever.
Okay, see if you like this. You like this? That's better. I like it. Yeah. Let's see what you mean. You're still learning how to use this space.
Yeah, I think you can pause that one, you know, the main light, so it doesn't come on so bright.
Ah,
Pause it.
Nope.
You just,
Well, why not?
Go for it.
It is my great pleasure to introduce our colloquium speaker today, Tom Kelly. Tom is an exceptional researcher and a very productive entrepreneur. He's the president and CEO of TEM Instruments. And I've known Tom for many years. In fact, when I was still in the game back around the late 90s, I got a call, curiously, from a venture capitalist company that said a fellow named Tom Kelly is interested in commercializing an instrument called the atom probe. What do you think about that? Well, I'd been in the game for a while and I'd seen atom probes tried to be commercialized, and they never really worked commercially. So I said, well, I don't think it's a very good investment. Boy, was I wrong. It turns out that a little bit later, in 2003, Tom introduced the first local electrode atom probe and sold it to Oak Ridge National Laboratories. And the rest, they say, is history. In 2010, his company, Imago Scientific Instruments, was bought out by Kamika, which is the business arm of a very large international corporation, Amatec. And they're now producing these instruments, the LEAP instruments, and they're in use all over the world. So I'm sure whatever Tom wants to tell us today, I'm not going to say it probably can't be commercialized. So,
Well, thank you, John. And it's always a pleasure to come to Albuquerque, and especially on a beautiful day like today. And thank you to everybody in the Department of Physics and Astronomy for the tour today, and I had a great time. So I'd like to start by noting that over the last 70 years or so, which is about my lifetime so far, there's been a lot of progress in atomic scale imaging. And in the 1950s, Professor Erwin Mueller at the Penn State University was developing field ion microscopy. And on October 12, 1955, he and Kanwar Bahadur were the first persons in history to see individual atoms using the field ion microscope. And about a decade later at Penn State, they're thinking, well, you know, it's nice to see them, but we sure would like to identify each atom. Like, what type of atom is that? And so he hired this guy, John Panitz, to figure this out. No one had ever detected single atoms before, but John had that task, and he built the first atom probe, published in 1968. A year later, Albert Crew and his group at the University of Chicago developed or showed imaging of single atoms with a scanning transmission electron microscope. So now we have a second microscopy technique, imaging single atoms. In the early 70s, John Panitz again developed what's called the imaging atom probe. And that was the first wide field of view atom probe. And it really opened up the atom probe so that you could see lots of material and look at the microstructure of materials at the atomic scale. And by the early 80s, the scanning tunneling microscope came along, and that too could see atoms on a surface. That was the third microscopy technique that could image single atoms. Later in the decade, the late 1980s, George Smith and Alfred Cereso at the University of Oxford took the wide field of view atom probe concept, and it needed a improved detector technology, and they were able to get it so that you could detect every single atom in a space or in a specimen. And that was a very big development as well. And of course, it was based on the ideas that John had put forward a decade earlier or more. And we get to the late 90s, early 2000s, and I started working on the local electrode atom probe, and we got that idea working so that the large field of view instrument at Oxford collected atoms at 1 atom per second, which at the time was great, but think of it, 1 million atoms takes you 12 days to collect. And 1 million atoms just does not much matter. You'll see some images today that are much bigger. We were able to develop the local electrode atom probe and get 10,000 atoms per second. So we 4 orders of magnitude increase in speed. And that's what really made the atom probe a practical tool. About that same time, aberration correction in electron microscopy became a reality, a practical reality. And both by Andrei Krivanik and Nicholas Delby at Neon Instruments correcting scanning transmission electron microscopes, and then Max Heider and Hal Rosa and Knut Urban on the transmission electron microscope. So for the most part, that's where we are today. A lot of very important developments in atomic scale imaging. What I want to talk about is what I think is an important possible next big step, which is in atomic scale imaging, which is what I call atomic scale analytical tomography. And we're not there yet, but I'm going to explain how we think we can get there and the path to get there. So, okay, Some reason.
Rehearsal.
Yeah, it was working.
Move the mouse to the extended screen. We click once.
Yeah. Oop,
Yeah, now it should work.
okay, I'll see. I just want to also note that we have some more collaborated, I'm sorry, I wanted to mention Brian Gorman and Simon Ring and I have been working on these ideas for over a decade. Thank you there. Also, Megan Holtz at Colorado School of Mines, Norm Salmon at Hummingbird, and Hamish Fraser and Dave Williams at the Ohio State University. We've all been talking about trying to pull together a project to get funding to develop one of the instruments that I'll be describing today. And so I want to give you a little bit more motivation for why and look at the role that scanning transmission electron microscopy. When I write this way, I mean either TEM or scanning TEM and atom probe, how they can play together nicely. And if you look at this instrument, I mean, this image, what you may see is atoms, right? Lots of atoms. Well, actually, and this is a high angle angular dark field image from a STEM. People in this audience probably know that those are not atoms, those are columns of atoms that we're imaging. They're probably about 50 atoms thick. So maybe 10,000 atoms in that image, or something like that. And what you see though is a lot of excellent detail, very high spatial fidelity, resolving the atomic lattice, even resolving this, which is a ferroelectric domain that is different in lead titanate deposited on dysprosium scandate from this recent paper from the Cornell group. So a lot of excellent information available there. But think about what happens if we happen to look at it, not in this view, but if we looked at it normal to that, say along this yellow arrow on the left. Well, that's what normally you see here. If the columns of atoms are aligned with the electron beam, you see nice resolved columns. But in the region in between, where this ferroelectric zone has bent the columns, you see a confused column or image. So, I mean, this starts to hint at, boy, it would sure be nice if we had three-dimensional information. Like, could we know the identity of each of those 50 atoms in that column? These are probably most likely the lead atom columns, but are there any impurities? Do those impurities affect the behavior? Do they segregate to this ferroelectric structure? And if so, where are they? And so this just hints at, even though the highest quality electron microscopes we have today don't get us everything we want. But you can do very nice things like really high quality electron diffraction. This speaks again to the spatial fidelity of the electron microscope. But most importantly, I want to note that the electron microscope also brings us chemical information. What I'm going to be showing you with the atom probe is compositional information. I make a strong distinction between that and chemical, where you're learning about chemical bonding or electronic states from spectroscopy, like electron energy loss spectroscopy. And so that's a very important adjunct I'll say more about, but that's part of the analytical part of ASAT. Well, on the other hand, there's the atom probe, and here's a high quality image from a nickel-based superalloy. This is about 100 million atoms in that image. All right, they're not all displayed because it would it's too much information. But what you can see here are large contiguous phases. This is the disordered BCC phase in the material, or FCC phase, and then in between, which is clear, is the intermetallic L12 structure, and inside the L12 structure are a lot of small disordered FCC precipitates. And it would be interesting to know the identity of every atom, and we have that from the atom probe. You can see indeed that it's a three-dimensional image. And one of the questions is there enough information there to take things to the next level? Like, could you in fact determine mechanical properties from information like that? I'll get to that a little bit later. One thing I'd like to point out is that this, I'm sorry, I think what I want to do is actually just explain how do we collect this image. Typically, you start by evaporating atoms from a sharp needle. These, let's say, if this end would be the first ones to evaporate, and you go through the specimen like that. So I'm going to show you schematically how this occurs. And the local electrode atom probe, or LEAP, as illustrated here, this might be the specimen. It typically is a conical shape. So there's a cone angle associated with that I'll get to in the next slide. But this is a counter electrode. And if you apply something like 10 kilovolts between the specimen and this counter electrode, you can create a very high electric field, which is high enough, and it's trying to pull positive charge out of that surface. So what actually happens is an atom on the surface, one of the valence electrons will tunnel into the specimen, and then that positive ion gets accelerated away. So it is a tunneling process. But the atoms would fly though to a detector. Now, if this detector can record the XY hit position, then you can keep track of that and figure out how to reconstruct where those atoms must have been back on the specimen. And that's what that previous image showed. One thing to know is that today's detector technology gives us about 80% of the atoms. It's based on microchannel plates being the first line of detection, and they only get about 80% of the atoms. And so that's something I'm going to address, because what we would like to have in these images is 100% of the atoms. So, but for all the beauty of that kind of image, there are some detractions, and this is the most serious one. That in the atom probe, we don't have a high spatial fidelity in general. And this is illustrated very nicely by some work by Francois Verpiot, who showed this is he created a specimen in a computer, all right? So he knows the identity and position of every atom in that image. And then he goes through a standard reconstruction using the protocols that have been developed for atom probe tomography. And I won't go into those, it's a lot of geometric stuff, but it has to do with the compression of the electric field as the ions fly away. But Q here is the detection efficiency. Typically, it used to be 60%, now it's about 80%, not 30%. But if you do everything correct, except you get the detector efficiency wrong, what you can see here is you get a different result, right? And in fact, not only is it expanded in Z, but these flat features are now curved, all right? And so this is a rubber ruler. There's another illustration. If you don't know the cone angle of the specimen, but you say, well, it's about 5 degrees, you can make some kind of guess, 8 degrees. Or if you put a large one, you can see the change of the reconstructed volume, say for a 32 degree versus, in this case, a 0 degree. So this is the effect of cone angle on the resultant image. And the bottom line is that this is not an acceptable outcome for imaging. We need high spatial fidelity. So we know that these can't be right. And what I think about this is that this is really unconstrained reconstruction. We don't have enough information about the specimen to properly constrain how to reconstruct it. And what we need is more information. And that's where the electron microscope should be able to come in. Well, let's go look at a couple more nice aspects of an atom probe. Here is a typical mass spectrum from that image I showed earlier. You might see there's a lot of peaks there, but actually they're all generally very well resolved. Notice this is a logarithmic intensity scale here. So this peak is 5 orders of magnitude above background. It makes this a very high signal to noise ratio technique. So you can get to high sensitivities. Atom probe will deliver 10 parts per million sensitivity for most elements, depending on the situation. It also, it's based on time of flight mass spectroscopy, so spectrometry. So you can see, for example, boron and carbon here, you can see lithium. We can even see hydrogen. In fact, those 3 peaks there are associated with hydrogen, hydrogen 2, and hydrogen 3. You can also see in the transition metals, some of the transition metal elements, these typically field evaporate as a +2. And then you can see some others here. There's the molybdenum, many isotopes. This is another very important thing. You see all the isotopes, not just the elemental identification. And in some applications, isotopic identity is essential and very helpful. Just finish out, there's a +3 of tungsten and a +2 set of peaks. All right, so once you are confident that you know what all these peaks represent, you can say, I'm going to identify the atoms that in this peak as tungsten and so on. And you can then reconstruct not just where the atoms were, but what their identities are. And so here's a smaller part of an image where you can see the different atoms displayed by colors. And if we take that, think about making slices in that. Let's say we take a 20 nanometer slice from that 3-dimensional image, and you can say, well, let me just show me these elements, aluminum, titanium, and tantalum. Those are the ones that tend to go to the intermetallic phases. Or you could look at the some of the other elements that tend to reside in the in this case a substitutional BCC phase. And so there's some powerful three-dimensional compositional imaging. And if we take this one step further, you can say, well, because you know where all the atoms are, you can calculate the local composition about any point in space. And so you can actually draw iso concentration surfaces. So for example, they're just showing there, now I'll turn off these atoms and you can see the iso concentration surfaces. So those surfaces surround a region, say, of high aluminum content, and outside it's a lower aluminum content, if you're picking an aluminum iso surface. And you remember all those precipitates we saw in that atom probe image earlier. I'll show it again, but let's say we wanted to know some information about that. That's one of the very difficult things to do in an electron microscope. You've got an embedded precipitate. How do you get unique information about what's in that precipitate? Well, here we can just isolate it in the computer. There it is. All right, there's a 4 nanometer precipitate. You can do that for each and every one of those in that other image. But we can go further. Wait, there's more. You can look at the atoms, just the atoms that are inside that precipitate, and you can actually look at the mass spectrum of that precipitate. You could do that for each and every precipitate or other phase. And in fact, there's the composition of that one precipitate in this case. And as I say, you can do it if you want for every one of the precipitates, and then start interrogating these kinds of images. So there's a rich three-dimensional character to atom probe tomography information. If we could just fix a few things like the spatial fidelity, and ideally this is only 60 or 80% of the atoms. In some cases, we'd like to have every single atom. So what is atomic scale analytical tomography? Well, if we could take the best of TEM by combining its spatial fidelity and analytical capabilities with the high analytical sensitivity by mass spectral analysis and the three-dimensionality of the atom probe or atom probe tomography. And then I would call that atomic scale tomography if what you're really after is the precise positioning and identity of every atom or isotope in this three-dimensional volume. We might also add that if you take the analytical information from the TEM, like the yields, that's where we, and this is very important, I would call that atomic scale analytical tomography or ASAT. So there's the definition. And then the question is, how do we get there? And who cares if we do get there? So this one slide is look at some of the things that you can do that would require that, or where this information would be valuable. So for example, certainly if you're looking at small objects, and 100 atoms is quite a small amount of matter, but if you're looking at quantum dots, for example, you want to know exactly where everything is. This does require knowledge of every atom in that structure. That's just one good example. And I know that there are groups that find that this is very important to, for example, for quantum work. And certainly on such small devices, if you have single atom devices, then every single atom matters. Think about if you've ever tried to determine, say, the radial distribution function of a material. If you know every atom's position precisely in real space, you can do radial distribution functions in the real space data. You can do it about any point you want. You can do it about any atom type you want with any other atom type. So it's all kind of rich information. And this kind of stuff is not available, say, from diffraction processes. And it all comes down to, do we have information about every atom with precise positioning? And if we're really gonna determine the design materials at the atomic scale, we're gonna need this kind of information at the atomic scale. In the long range, Brian Gorman and myself and Simon Ringer have been talking about this, and we think it's realistic to talk about this. It's a long distance from here to there, but to talk about determining physical properties from atomic scale data. If you know every single atom in a, maybe not 100 million atom image, but 100 billion atom image, then you can start doing data mining, correlating it with the physical properties. That's a large enough sample of the material that you could potentially predict its mechanical properties or other physical properties with precision. I think we're still a few decades away from that position, but that is where you can see over the horizon we could get there. One other, if we're going to do atomic scale mapping of organic and biological materials, we really do need 100% of the atoms, because if you're missing a carbon or nitrogen, that changes everything. So that's one area where it would be very important. And finally, imagine trying to engineer materials for fusion reactors on the first wall. There's all kinds of things going on with defects being generated, daughter products being generated, and grain boundaries, dislocations. And could we, if we really get 100%, then any missing atom is a vacancy. Well, I don't have any delusions about the fact every scientific experiment has some noise. So the question is, how low can we get the noise? Can we get to 99.999, or who knows? Until we understand that better, we can't really be claiming to know whether we can map vacancies, but I do think it's something to be looking for in the future. All right, so what is a little bit of the history here? How did this all come about? Really, it goes back to a lot of conversations and thinking in the atom probe world, in my view. And I, for a long time, felt like, gee, we've got this technique that pulls the atoms off, and then we throw 40% of them away. And it's just because of the detector. We did not have detector technology that could detect them all. So I had been looking for a long time, is there a way to get 100% detection efficiency? And I remember reading this paper by Kent Irwin, who's at the time was at NIST Boulder. It was in Scientific American, and he's explaining why superconducting materials make exquisitely good detectors. It's because superconductivity is so fragile. If you had something operating at 5 Kelvin and you put a tiny little heat in, it goes normal, and that produces a big change in its behavior. So, and I'll explain how we might use this. So anyway, I started thinking about this. I contacted Kent. Do you think we could use this to build a 100% detection efficiency? And he suggested, and I'll show you the next slide, that I talked to some people at the University of Wisconsin who he knew that worked in these kinds of areas. And anyway, well, I'll just finish by saying that superconductors, I do think we can get to 100% detection efficiency. It's actually been demonstrated already, not by us, but some others. If you remember that the Cooper paired electrons travel in a superconductor with a band gap on the order of 5 millieV. So what would the signal be? And I'll explain this, but if you send in a 5 keV ion, which is a typical number, you're going to break apart 1 million Cooper pairs. That means there's 2 million electrons that are free and not bound as Cooper pairs. That's a huge signal. 1 million electrons is more than enough in a electronic circuit to detect readily. So it's a large signal, large enough that you don't even need external amplifiers. It's self-amplifying. And all of this happens in 40 picoseconds. So if we're going to make an atom probe detector, we need timing resolution. This has the horsepower with the timing resolution to deliver. I'll say more about this in a minute. So what this led to is, I'm thinking, wow, we could really, with some work, we could develop the superconducting detector and get 100% of the atoms. And then the only thing missing in the atom probe is the rubber ruler problem. How do we fix that? And this is what really led to, can we fix it by getting information from an electron microscope? And so I got together with Mike Miller and Krishna Rajan and same Simon Ringer back in the 2010 timeframe. And we started talking about this, and we also went to Neon Instruments, Andre Kravanek and Nicholas Delby. Could we get a big project funded in the United States to try to build an atom probe inside an electron microscope? Here's the basic idea, that you've got an atom probe specimen right here on maybe on a side entry holder. This is a drawing from this paper. We want to extract the ions out to a detector. But we're using the electron microscope to image the needle and get information about the shank angle and all kinds of other good stuff. Anyway, that did not get funded in the United States, but we wrote this paper, and I subsequently wrote this other one. We were hoping by 2020 we would have a working instrument. Anyway, that's a lesson we can all take. Things always take twice or 3 times as long as you hope. But the vision that we put forward was that atomic scale analytical tomography would be achieved by 2020, where you would have 100% of the atoms detected, and the atom positions would be known with high precision. And so that's what this is schematically trying to illustrate. We felt you could get to billion atom data sets, and I do believe we will readily do that. I'll say more about that later. And then if you integrate the analytical information, then you've got this powerful information. And if you also realize that coupling these very high quality images with computational material science and engineering would provide potentially a very powerful feedback central mechanism where you have computational material scientists able to finally get their hands on high quality data and maybe extract more information from the data generated. So what does that look like? Well, imagine you've got let's say this is just an image of a device from a STEM, and if you add analytical information like electron diffraction and maybe some atom probe data from a transistor structure, and you're able to achieve atomic scale tomography. Now we know the position and identity of every atom in 3D, and it's a large volume. Then you've got this nice outcome. But if you can add the analytical information like the yields, maybe EDS, of course, and perhaps couple it with some electronic structure calculations, then I would call that atomic scale analytical tomography. And then actually, once you know all of that information, well, that's when you can start to say, well, can I calculate the transconductance of that transistor and get it correct? Can you determine properties from the microscopy? In other words, can you perform structure properties microscopy, not simply structural microscopy? By the way, once you know where all the atoms are, you can just calculate what the image that you just recorded in the electron microscope should look like. That's a straightforward project. So you can have a feedback mechanism that, yes, I am getting the same result in the electron microscope and in the calculated outcome. So we did not get that project funded. That was called the Atom Project in the United States. And in 2014, I was talking to Dirk Rabe from the Max Planck Institute in Düsseldorf. And he said, whatever happened to your Atom Project? Did you guys get funded? And I said, no, we're still thinking about it. And he said, well, what about, do you want to try to get some funding in Europe? So I said, all right, I'm game. And he brought in the folks at Forschungszentrum Jülich, which is one of the premier electron microscopy labs in Germany, and Rafał Dany-Borkowski and Joachim Meyer, and also Max Heider at CIOS. And we started working on a proposal. We submitted it in 2015. It was mostly these folks that had to do the submitting, but I was pretty involved in developing it. And this was called Project TOMO. Well, it took 4 years to get funding, but it did get funded. And so in 2019, it got funded. I was involved in helping sort out who was going to produce the electron microscope, who was going to produce the atom probe inside. But in the end, Thermo Fisher Corporation was awarded the contract to build an aberration corrected 300 kV STEM. Kamika is the company that is building the atom probe. And so they're going to build an atom probe inside that 300 kV column. And it should be nominally delivered late 2023 or by the end. Unfortunately, the funding for the superconducting detector fell through. And this was an unfortunate situation. Originally it was in there, but anyway, so they still hope maybe someday they can replace the detector on there. And so this will be everything but 100% detection efficiency on that project. And just to finish up the development of ASAT, Simon and Brian and I recently finished a book on this called Atomic Scale Analytical Tomography, and I have a copy of that here right now. And actually, this is a copy for my buddy John.
Thank you.
You notice who wrote the forward there. Thank you for that, John, and appreciate all your mentorship. And John is actually an advisor for our first company on the local electron atom probe. And so, anyway, we in this book we spent a lot of time looking at how could you achieve ASAT, and who cares if you do? What are the applications? And then, what are some of the scientific frontiers? So we sort of 1/3 looking at how do you get there, 1/3, who would use it, and 1/3 looking at where could this go. So, all right, I just want to say one last thing here that in atomic scale analytical tomography, I think it's quite important to take the approach that we're trying to achieve perfection or eliminate all errors. so that we know where every atom is with high precision. The reason is that we know a lot of information already, but I think we have to keep striving for, can we get 100%? If we want to map vacancies, which would be huge, for example, that would be something we have to keep pushing for in this process. At any rate, I do think that it's not a question of will ASAT ever be achieved. I think we're getting closer and closer every day. It will be achieved. The question is when, and in fact, how perfect will it be? Which is partly what I'm getting at up here. That early on it probably won't be as perfect as it will be after 20 years of development. But I think if you see that this approach to atomic scale microscopy, where you're generating images with very large number of atoms, where you know the position with high quality, then anyway, the degree of perfection will be an important point there. All right, I want to say a little bit about the technology on the detector first, then on the electron microscope, and then I'll say a little bit about some potential applications. At any rate, just to give you an idea of how would one of these superconducting detectors work, it's based on the concept of a delay line detector. And this would be, let's say, a micron wide line of niobium, which is a superconducting material at 9.7 Kelvin. And it'd be about 40 nanometer thick. And if you put a supercurrent in that at 5 Kelvin, all right, about at half the critical current density, then you have this wire just sitting there superconducting. If energy comes in the form of an ion or an electron or a photon, that energy, and I'll show you this in the next slide, will disrupt the superconducting Cooper pairs, and it behaves like a change in impedance suddenly. And what that all of a sudden these Cooper paired electrons are happily floating along with no resistance, and all of a sudden there's a hot zone with a lot of resistance. All of these electrons come in this way, or if the current's going this way, or the electrons are going this way, they back up and it creates a negative pulse, and then that propagates away from the event. And this propagates at the speed of light in this medium, which would be about a quarter the speed of light in vacuum. And then if there's a negative pulse going this way, then has to be a positive pulse going the other way. So how do you detect, first of all, how do you detect if there's a pulse? Well, all you need to do is put a sensor at the end, but actually we want to know where along this line did the energy hit. And so if you put a clock at each end, then you look at the time difference between the two clocks. If the time difference is 0, it must have landed in the middle, and a positive time difference gives you some position on the right, a negative time difference position on the left. Also, you can use these to interpolate the hit time. So basically, the average of these two clocks is the correct hit time. And so you get sum gives you the hit time, difference gives you the hit position. So then let's say, okay, we need to fill an area, not just a one-dimensional detector. We need a two-dimensional detector. And let's say that's the area that we need to detect ions hitting. Well, you could put a meander electrode, and this would this is actually this is Robert McDermott is the professor of physics at the University of Wisconsin, and Joey was his graduate student who graduated actually in 2018 now. But I supported this work when I was at Kamika, and he built these lithographically at the University of Wisconsin. So this is a one-dimensional meander delay line superconducting detector. But that if you get a hit there and you can resolve where, that gives you the X hit position. I'm sorry, the Y. So how do you get the well, and by the way, these are roughly 1 micron period, actually 1.5 micron. So if you notice here, you do the math, you find out that is a very long wire. It's 2 kilometers long with a 40 micron transit time end to end. And that becomes critical. When we try to make larger and larger detectors, we're going to need to take that into account and break them up into smaller modules. But how do you get a two-dimensional detector out of this? Well, and this is an actual one. You overlay an X meander on top of the Y meander. There's a thin dielectric film between them. And this is an actual device where you can see the wires come in on the Y meander and go out, and then the X meander. And these work. The biggest challenge is the lithographic cleanliness, making sure you don't give any shorts or opens. And so you might be wondering, how do you get 100% detection efficiency when you have a large open area ratio like that on wires pattern? Well, if an ion comes in, it hits, and actually we put a dielectric absorber above this is the X lines coming in and out of the page and the Y lines in the page, all right? And then there's a ground plane below. All of this is operating at 5 Kelvin. And so the energy comes in, it creates a phonon shower. To first order, it's spherically propagating away from the hit position. And so this wire is seeing energy on both of those. And so even though it hit between the X lines, it's actually generating a signal in the X line, and similarly with the Y line. So that's how you get 100% detection efficiency. And actually people have demonstrated this in slightly different, they're the same general category, but not for ions. And at any rate, so you can indeed get 100% detection efficiency, whatever 100% actually means. And we've been developing these things, and here's just a brief overview of that. This is on a high purity copper carrier. We have a circuit board that this is a 10 millimeter by 10 millimeter square superconducting delay line. We call them skittle. In fact, you hit it with an ion, you can see there's a fairly robust, this would be several millivolt signal. In fact, this is actually recorded on a 200 megahertz oscilloscope. We needed more like a 500 or a gigahertz scope to do justice to this, but it's a very robust signal. And so we're still in the process of scaling this up with lithographically and so on, but you can see that we do expect it'll be challenged to prove that it's 100% quantum efficiency for ions in an atom probe, but we've actually demonstrated better than 200 picosecond timing resolution. So the timing resolution that's about what you want for an atom probe. It's excellent. These things will have very high pixel resolution on the order of 10 micron per pixel. So that means a 22 millimeter by 22 millimeter, which is our target at the moment, will give us a 2K by 2K sensor. With robust signal to noise and so on. This is quite important because I'll just say this briefly now. Atom probes use a conventional copper wire delay line that's significantly larger, up closer towards a millimeter in size, but the pixel size is a very large fraction of the detector. And the problem with that is that if you have two ions evaporate next to each other, they cannot be resolved as a single hit. So you get multi-hit losses. So you've tried very hard to avoid multiple hits or multiple evaporation events. And so the bottom line is the best state-of-the-art atom probes today operate with a very low or very sparse evaporation probability. One pulse in 100 pulses produces an evaporation event in a typical operation. So this is, if we can resolve both events or even 10 events per pulse, then we can run that up to, say, not 0.01 atoms per pulse, but we can run it 1 or 10. This is 1,000 times higher data collection rate. So atom probes today are doing 10 to the 4 atoms per second. I think in a few years we'll be showing 10 to the 7, at least 10 to the 6 atoms per second. And so billion atoms will take 20 minutes. And so now you can start to realistically think about billion atom images and doing data mining on much larger data sets. All right, enough of that. So how do we get the positions of the atoms to high precision? And this is the role that the electron microscope would play. And I want to give a lot of the credit to this particular figure to Brian Gorman and working with Megan at Colorado School of Mines. We've actually got 2 or 3, we think, viable ways to fix this. I'm just going to show you this one because I think it's the most exciting at the moment. And that is using 4D STEM to get the atom positions in the specimen before you field evaporate it. And I'll explain that now. So what he's going after is basically, and by the way, 4D STEM is all about, you've got an electron beam hits a specimen and it produces a diffraction pattern, a nano diffraction pattern. If you record that in a pixelated STEM detector, not just simply something with an annular symmetry, but pixelated, as you can see, even the individual pixels in this. Then you can start to use that as a coherent diffractive imaging approach and reconstruct the image with those types of approaches. And I'm not going to go into coherent diffractive imaging, but I go into this a little bit more. And in particular, this is a very nice paper by Paget et al. This is from the Cornell group, very recent, where they look at coherent diffractive imaging using exit wave power spectrum. And I'll explain that very briefly, which is that you get that nano-diffraction pattern. If you take its log, it actually makes it a lot less sensitive. It suppresses things like tilt and thickness effects in the result. And if you take the Fourier transform, the fast Fourier transform of a logarithmic of a log of a diffraction pattern, you get back to real space. But you get basically a very high quality representation of where the atoms are about some central point. And this can be used to very precisely locate the atoms in the specimen. And the way this is done is you defocus the probe to maybe 5 nanometers. You want to map something, let's say you want to map something that's a micron, you do a 5 nanometer spot, then you move about 2.5 nanometers and do it again, and again, and again, and again. Then you mobile on, or step scan is another word for it. And that might take 1,000 patterns, but you can record these at, some of these cameras are doing 10,000 images per second. Okay. Hang on. Technical difficulties. And anyway, in 1 second, you can get all the diffraction patterns you need. It takes another minute for the computer to crunch it and give you a very high quality image. At any rate, I won't go into a huge amount of detail here, but this is the exit wave power spectrum. These are the nano beam electron diffraction. So that's reciprocal space. Down below is back to real space. All right, those are atom positions. But down here is the, you can separate that and look at, if you go back to reciprocal space from just that information, you see that is correlating roughly with the large spatial or reciprocal space frequencies, and also here. At any rate, what we're more interested in is the atom positions away from that center. And so what you see is a very high quality rendering of the spatial frequencies recovered in real space. At any rate, the bottom line is here that this approach, as I say, that Brian and Megan have been developing, it has demonstrated better than 5 picometer precision for the atom positions. It's a mind-blowing precision, but it's I've seen this multiple times. And you get the 3-dimensional positions of the atoms from this approach. And I'll show you another example in a minute. And it's fast. So, I mean, if you have a fast camera, that is. So you're looking at something like 10 to the 4 diffraction patterns to cover an area. And that can take all of a second to record that. And then you've got a little bit of number crunching and you're done. Another really important point is it requires about 1,000 times fewer electrons than if you tried to record that similar information with the standard STEM approach. And also, you're defocusing to 5 nanometers. You don't need aberration corrected optics for this. So you could, in fact, you could do this probably in a very straightforward column, which is not to say you don't need aberration corrected microscopes. If you're thinking about building a combined atom probe and electron microscope, you don't want it to be any more complicated than necessary. So if this is good enough to give us those results in a combined instrument, that is a very attractive way to go. And finally, it doesn't require precise alignment because this exit wave power spectrum is very insensitive to small changes in tilt, unlike imaging down zone axes. So here's a couple of examples, and I'm just about to finish. Brian and Megan were looking at silicon germanium quantum dots in this kind of structure that's embedded in, they created an atom probe sample by fib milling. Ignore this stuff up here, but you can see the quantum dots. And in fact, if you look, the 4D STEM results give you, and I'll show you this in the next slide, they give you the displacement of the atoms away from, say, a nominal 5.5 angstrom. So this is a vertical displacement, this is horizontal displacement, and in that one, one area. In fact, you can see the distribution of atomic displacements relative to, say, the ideal at 5.5 angstrom. In other words, this is given really high precision, three-dimensional atom positions from interior even of an atom probe specimen. And so this does suggest that it is a promising way to achieve atomic scale analytical tomography so that we could map these three-dimensional atom positions using 4D STEM exit wave phase power substrum. And then the challenge, and we don't have this all worked out yet. This is where, now you know where we're at, the bleeding edge. Can we correlate these indeed at every, with zero error, if you will? Can we correlate the atom positions that we've just determined in the electron microscope, then we rip the specimen apart in the atom probe? Can we put those two together? Certainly, if we have 100% detection efficiency, that should help this correlation. But this work is very early and ongoing, and we'll see how that all plays out. But I think there's you find some fiducials, smart people are working on this. I think it'll get done. At any rate, hopefully then we will have the atom positions and the specimen shape all achieved. And we know that the result is correct because you'll use an electron microscope to verify. And then, hey, we got the isotopic identities of every atom in that large volume. And as I mentioned earlier, we're starting to use the B word, billion atom images, and not just satisfied with 10 or 100 million atoms. John used to do 100 atoms in a night, right?
Yeah.
And well, progress. All right, I'll finish up. I don't want to spend too much time, but this is similar work from Brian and Megan on a oxide. Well, it's in germanium. I think there's an oxide layer here. I realized I didn't spend a lot of time on preparing this part. It's their work, but what you're really getting, you can see here that you're getting the atom position displacements from ideal in the lateral and in the longitudinal direction. And what's especially important is he's focused on this region right here, right below the oxide layer. And so this is an atom probe that was into the TEM before, the specimen before it went into the atom probe. And then after the atom probe, all of that material had been field evaporated. You can see the nominally spherical surface after evaporation. And if you look at this is a particular image. If you look at the atom positions determined near that oxide layer, you can see that this shown here a very high quality rendering of the atoms. This is one of the challenges of rendering so many atoms is that they're overlapping each other, but they have indeed determined the atom positions, and they're starting to work on the question of how do we make sure we're correlating them with the atom probe data. They don't have 100% detection efficiency yet. I think we're still a year or two away from having that working in an atom probe, but that's coming. So I think last two slides. In that layer, there was there's an oxide layer, but there's germanium at this interface. And at any rate, I think I didn't want to show this one. This is the last one I want to show before I conclude. On another topic, this is from some work that Katie Rice at CAMIGA did a few years ago. And you see a beautiful image of a grain boundary, right? That's a grain boundary. Everybody agree? How do you know? If you were a reviewer of this paper, would you let me say that's a grain boundary and let me get away with it? Because I don't have any proof that that's a grain boundary. It looks like a grain boundary, but all right. This is, I'm really getting at, we've heard this argument too many times. You try to say that's a grain boundary and the reviewer says, oh, you can't say that. How can you prove that, right? But all right, well, what Katie did, she's got a EK or a TKD, a transmission Kikuchi pattern detector on her fib at CAMIGA. And so one of the things that when they're preparing it, they take time. They're actually trying to find a grain boundary for the atom probe analysis, and you actually can get diffraction patterns. In this case, pixelated as shown here. And so there's a Kikuchi pattern obtained from, say, one of those spots and this is directly corresponding to this. So not only do you know that, in fact, in this case, we do know that is indeed a grain boundary. We actually, she has the information that shows what the relative orientation relationship is and other things. So it is a quite high quality result. And my point is that if you're ever doing this kind of work, you really ought to be prepared to back up that that is indeed a grain boundary by some other hard evidence. All right, so it's a grain boundary. What do we know about it? Well, in nickel-based superalloys, 40 years ago, people figured out that if you put boron in these things, you can improve their creep resistance, but you create other problems. And boron is known to create, I think, some brittle behavior. And so it's a blessing and a curse. And so the question is, how is it doing that? And basically people started finding, they think it was at the grain boundaries. Well, Atom Probe has been able to show that very nicely, that indeed in these nickel-based superalloys, the boron does tend to very strongly segregate to the grain boundaries. But it's not the only element. As you can see, titanium, silicon, and carbon also are segregating there. But then wait a minute, how do we know that? Is that the cause? Just because I see boron on that grain boundary, does that mean that that's causing grain boundary embrittlement? Well, could you say anything about the bonding at that boundary? Has that affected it? To me, this is what I'm getting at, is that in this work, Katie didn't have that, but if you have this in the electron microscope, one of the first things you want to do is say, okay, can we get yields information? Tell us if the boron is, or these other elements are affecting the bonding across that interface. This is making the point that you want to have chemical information supplementing just the raw compositional information if you're really going to be able to draw hard scientific results. So at any rate, with that, I will conclude by noting that I think by combining electron microscopes with the atom probe in a single instrument, we do expect that we'll generate three-dimensional atomic scale images, and that we will be able to precisely position every atom and eliminate that rubber ruler problem in the atom probe. It's also great that atom probe delivers isotopic identity, so we have compositional isotopic information, and the electron microscope delivers that chemical information. We'll see more and more how I think that will be important. So I would say I do believe that ASAT will have a major impact on atomic scale endeavors, might even have impact on the landing gear of the jets you're flying in a few years by determining mechanical properties from 100 billion atom images. And at any rate, I will finish by saying I expect we will see working ASAT instruments somewhere in the next 5 years. So that's how far we are away. It's taken only 12 or more years to get this far, but it always seems to take 20 years to bring in new technologies, right? And I'll finish with a quote by a famous 20th century philosopher who said, without deviation from the norm, progress is not possible. And I hope to leave you with that. Does anybody know who said that? Frank Zappa, my hero. All right, thank you I appreciate it. Do people in Zoom get to ask? They can just shout out. I don't think so.
Well, in that case,
Yeah, I have. Who's asking first? Sarah.
Sure. Yeah, so I think it's really interesting how you might put together this. Okay, I'm gonna get the acronym wrong probably, but EWPC
Yes.
and APT.
Yeah.
But I guess I don't quite see how. Can you give a sense of? You said it's still under progress, and so you're still working it out. Can you give an example of how that might work?
Yeah. All right. So let's say you've got the atom probe specimen and we do the diffractive imaging. So you get the atom positions. So actually, the atom positions for every atom in that volume you just analyzed. You just don't know their identity, right? So if you then go to the atom probe, if you have 100% detection efficiency, then every atom in the atom probe data set must correspond with one of the atoms in the EWPC. So are there any fiducials that'll say, okay, this is a planar feature here, it has to show up as a planar feature over there, or things like that. So those are the kinds of things that we know that the volume constraints and the length and things like that are the same. And so we'll have that. And I mean, this is where we're at right now. And in fact, I should say that Brian and Megan have been thinking on this for 2 years, and could probably give you a more solid answer right now. But I do know that let's say it was not a homogeneous material, but if it's precipitates, you can see those in the electron microscope, you see them in the atom probe, and you overlay them, and you have the computer keep refining. And if you imagine getting that right, then I think that's probably the easier one to start with, and then we start tackling more and more subtle approaches. So does that get you an answer?
Yeah, I think I see some of it anyway. Thank you.
So I have a question about finding the location of the atoms. From the little bit I know about field emission microscopy, you can sort of figure out where things come based on the curvature of your tip, where the high field is, and things go radially off from that.
Yep.
But from the images you were showing us here, it appears that you may start with a sample which has a tip on it, but then you start pulling atoms off, and eventually you don't have the same tip anymore. So don't you lose your spatial information as to which way the atoms are going to go at that point?
Well,
How do you keep up with that?
so typically you've got a counter electrode that's 50 micron away. And we've got a needle here that we've just removed 100 nanometers. So that change, in principle, yeah, you could have this on a stage where we keep moving the specimen to make up for that change in flight length, but that's too negligible at the moment. If we start running off 2 micron out of 50, maybe we need to have a motion, but still the electric field distribution is indeed changing. And so if it's sharp initially and then it gets blunter, that indeed, that still projects out onto the same detector. And this is well known in this world or this field where you have a decreasing magnification as you run down a conical.
So you just account for that?
Yes, absolutely. I mean, you should see some of the accounting that people do. It makes you worry because it looks too complex at times. I'd rather see something really simple and clear. But I mean, I just highlighted very briefly the kind of reconstruction mathematics that are used. And
so also the electron energy loss spectroscopy. If I remember, is this where you send say high-speed electrons in the proximity of a metal surface, and then they come out with less energy than they
yes.
in? And so do you send that by the surface of your probe tip?
Yes. So let's say there's a specimen and electron beam is vertical coming through. There's various ways for the electron beam to lose energy in the specimen. Generally, it doesn't gain, although there are gain mechanisms actually, but it can excite characteristic losses. So knock a 1s or a 2s electron out. That's a well-known amount of energy, and you'll see characteristic change 400 for EV for nitrogen K shell, for example. So if you look at the electron beam is let's say it's 100 kilovolts plus or minus 2 volts, or some very small energy spread. You'll see at 400,000 minus 404, you'll see there's a lot of electrons that have lost that much energy. So there must be a lot of nitrogen in that. So characteristics are one thing. There's also collective losses like plasmons, both bulk and surface plasmons. So anyway, those are the electron comes in and they push electrons away, and then the electron flies through, and then they come back and boing, 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 basically a reverberation. Those kind of collective mechanisms can tell you other things about what's going on in the sample, but for the most part, it's so once the electrons pass through, then typically you use a magnetic sector to separate them by energy, and in the early days, they used to just serially scan across a pair of slits to see how the signal varied. But now they do a parallel recording, so you collect everything all at once.
So in the case where your tip surface is an inhomogeneous, there's this kind of atom here and this kind of atom here, you're just getting some kind of average energy loss.
Oh, yeah, yeah.
From the whole thing.
That's right. It's characteristic losses tend to be highly localized, and collective losses tend to be delocalized. You can even have what's called not phantom. You can have an electron being passed by and excite oscillations and lose energy without ever passing through the specimen. Yeah, so people have demonstrated with these aberration corrected microscopes, you can focus a probe to 100 picometers or even smaller, position it with that kind of precision in a specimen where you see in the electron columns, and you can see excitation of, say, the gallium and the nitrogen independently in an energy loss spectrum. So you look down the nitrogen columns or the gallium columns or things like that. So it can be highly localized depending on exactly what you're doing. What I would envision being of most interest is especially if you want to look down certain crystallographic orientations and get some chemical information that is maybe guided by what the theorists are trying to calculate, and say, if you can give me that information, then we'll see if that matches off prediction.
How will you know when you reached 100% efficiency?
Oh, great question, because it's so hard. I'll give you one example. If you, we see the lattice, all right? So we know in tungsten what the lattice parameter is. If I give you a very simple example, and let's say we take some large volume, and because we can see the lattice, we know how many unit cells in each direction, so we know the volume. Then you just count how many atoms are in that volume. We know how many should be in pure tungsten. So that's one way. Whether that will pass muster in a review community is yet to be demonstrated. But it's not easy to be confident that you've measured 100% detection efficiency. So it's out there as a challenge. But that is one way we will try. Another way is like if you fabricate multi-layered structures, and you can do it with molecular beam epitaxy and be very precise, and then you should get the correct thicknesses and all that. But you can always attack that and say, well, how do you know it was that thickness? If you're trying to measure to some high precision, it's not going to be easy.
I have a question as well there.
Any questions on Zoom? The chat question.
Maybe similar.
Yeah, I hear me. It's the same question in the chat. I'm just interested in what specific or critical problems at the forefront of semiconductor developments might be waiting for these instruments.
We've actually had some very good conversations with people at Intel. They are a bit worried about the future of developing 3 nanometer node devices, and how are you going to know what you just made? You can spend $10 million on an instrument and you turn the knob to 11 and cross your fingers, right? How do you know what it's doing? So you've got to have that feedback mechanism. And I mean, the electron microscope can do a lot of it, but they say they see limitations in what they can do to characterize these devices with an electron microscope. It'll still play a huge role, but they feel like this is going to be this is the kind of technique that they may need for certainly some very small devices. And they're even they're looking at stuff like with single atom functionality and stuff like that. I wouldn't want to be the one trying to characterize a single atom transistor with 60% detection efficiency. So you got to look at 10 of them to see if you see 6 atoms. I don't know that I'm in the best position to give you a detailed answer, but I can say that as I said, we've talked to Intel, and at some level they don't really want to spill the beans completely as to what they need. They want to tell you enough so that they can get what they need down the road, but it's a daunting challenge to be making these devices in the semiconductor industry at the nodes that they're doing right now. And yeah, I do think that there's some things like some of the dielectrics, you can have a 1 atom thick interface layer that can change the behavior, and you need to know details about that. And if you're looking at a very thin layer like that in projection in a TEM, you don't necessarily have the detailed information that they really need there. So that's just one example, maybe.
Great
Yeah.
talk, Tom.
Adrian.
Fascinating. So you said the first STEM APT will be like 2023 sometime? Is that the prototype, proof of concept, or is it being installed somewhere? Or?
Yeah, so Thermo Fisher, the schedule for Project Tomo is that Thermo Fisher and Kamika, they've already actually, I think, bolted the atom probe onto one of their columns, but there's a lot of testing and all that. I think their intent is about a year from now to deliver a first item to Forschungszentrum. And it may not be the final one. They may want to get it there and have the people at in Jülich use it for another year. So I was involved in this right up to the point where the funding for the superconducting detector fell through. And then it's like, well, there's no reason I should be on that if there's commercial interest, and I'm in a commercial side, you know, so I don't really have firsthand knowledge of what's going on anymore in that project. But I mean, they're willing to say things like, yeah, we're on track for the original schedule to deliver the first item and stuff like that. Yeah.
How was it getting Kamika and Thermo Fisher to work together?
It's actually fine. They both, I mean, you know, a Spectra 300 double corrected column, and you're gonna do what to it? So, I mean, that's the first reaction, like, okay, and so, but the people at Thermo Fisher and Eindhoven were kind of excited about the project, you know, and so that was all good, and so they're pursuing it, and so it actually was good. We had a lot of good meetings, and you know, and same with at Kamika, the engineers love doing new stuff like this, and so it was a good mood, and I think but they had to be careful, like telling. I mean, for example, one of the reasons that the funding for the superconducting detector fell through is that they had to put it into a different funding year, and so they had to get the two big ones committed first, the column and the atom probe. All right. So both of those companies have a contract that says you're going to build this and deliver it by this date and meet these specs and all this stuff, right? This is a lot of many millions of dollars involved. And so then they say, okay, now you guys, we got to get a contract with this little group in Madison that's doing, and you're gonna do what? You're gonna put a cryo compressor on our Spectra 300 double corrected column? Like, no, we don't think so. And so then it became a complicated question of how does Thermo continue to guarantee performance when they don't know anything about this newfangled detector? And honestly, in the end, time ran out. It was like too many things to get resolved in too short a time. And unfortunately, the money they got to fund the superconducting detector had a time limit. It had to be spent by this date. And anyway, that's why it all fell apart, which is why they still hope maybe we can do it. And so those were just more like the engineers were happy to try to make it work. But you get, I'm not going to blame lawyers. I'm just going to say that the management that had to watch after Thermo Fisher's interests, you know, did what they had to do, and you understand that they had to do that stuff. But, you know, how do we know when you bolt that on, we're going to be dead in the water for who knows how long?
Let's thank him again.
Yeah. Thank you, everyone out there in Zoom land, yeah. So now we have beer. I know, yeah, thanks. And, yeah. Well, I should tell you what, yeah, that's switch, but. Stop here.
The testament assumes you have 100% ionization.
Yeah.
Yeah.
I'd say everybody.
It's not true.